equilibrium, and we're looking at page 29. So we finished with letter B here. So if you look at letter B, let's just kind of kickstart you guys a little bit. It says calculate the value of the equilibrium constant at 127 degrees for the reaction. All right, so if you look at this, we started off on number 1, exercise 3A, and we have the Haber process where it's N2 plus 3H2 produces 2NH3, so the Haber process. And so we wrote our equilibrium expression, and then we plugged the numbers because they gave us amounts of substances here. So we plugged the number in, and we found out what K was. Now, once we found out what K is, what they're doing on part B is saying, okay, now flip it. Here's our equation that we started with where we're going towards this direction. Now what's K going to be if we go the backwards direction? Because typically K is the forward in the forward direction here, right? That's typically what we're looking at. So now when we have K in the reverse direction, we've got our K already. It's 3.8 times 10 to the 4th. How do we find it when it was going in the reverse direction? If you go back in your notes, way back in your notes, to page 14, what do we do if we alter the chemical equation? So if we change the stoichiometry, it alters the chemical equation here. If we multiply it, if we reverse the equation, we've got K already, it's 1 over K. So if you do the reverse equation, then it's 1 over K. So that's page 14, you might want to mark that somehow. So here we've got K. So if we reverse the reaction, we're going to have 1 over 3.8 times 10 to the 4th. Here is our reverse. There's nothing on your green pages that says this. I don't think so. So those are things that you're just going to have to remember. So we have our equilibrium. Nothing here tells us, well, what if we reverse the reaction? So if we reverse the reaction, it's going to be 1 over K. Pop that in your calculator. And I'm going back to page 14 to look at those again because this is what we're doing. When we mess with the equation, the chemical reaction, what do we do here? So we reverse the reaction, we do 1 over K. The next one says, okay, now look at what we're doing here. We had our original equation, 1N2 plus 3H2 produces 2NH3. And now if you look at this next equation on letter C, everything is divided by 2, isn't it? This was a 2, so it's divided by 2 is 1. So basically we have divided by 2. If we look on page 14, if we multiply the reactions, then it's raised to the n power. If I divide by 2, isn't that the same as multiplying by 1/2? Yes? So if I multiply, then I'm going to raise it to that power. So if I, instead of thinking of it as multiplying by 2, as dividing by 2, I could say it's multiplying by 1/2. So I'm going to take my K, 3.8 times 10 to the 4th, and I'm going to raise it to the 1/2 power, which, in other words, is known as doing what to it? Yeah, you're taking the square root. Or you could pop it into your calculator. If you don't remember that raising it to the 1/2 is a square root, you could pop it into your calculator and raise it with that little caret button to the 1/2. It's strangely the same thing. So if we reverse the reaction, we take the reciprocal, 1 over whatever our K was. If we multiply it by something, that's what we're going to raise it to. You could calculate the whole thing over again. You know how we've got this? Yes? We have our equilibrium expression. You could change it and put this to the 1/2, this to the 1, N2 to the 1/2, and H2 to the 3/2, and you could calculate it all over again. It'll work just the exact same. But it's easiest if you just say, hey, I'm going to take my K and I'm going to raise it to whatever power I'm multiplying the equation by. Okay, exercise 5. what are the equilibrium expressions for these equilibria? Okay, so we've got A plus 3B produces AB3. And again, I don't know why they didn't put things as a subscript. Maybe, I don't know, someone who's doing the paper couldn't figure out how to do that or not. But that's a subscript right here. So when we write the equilibrium expression, products over reactants, notice everything is a gas. So our K, and I'm going to put KEQ just to be generic. If I put KC, that would be the concentration. If I put KP, that would be a gas pressure, right? So here I've got KEQ, products over reactants. So I have the concentration of AB3 products, and it's raised to the 1 power, divided by the concentration of A times the concentration of B, and B is what? Cubed. That's the equilibrium expression. Remember that? Do the other two. Do number 2, and then I want to talk to you about number 3. The equilibrium expression has an equal sign. You don't just simply write this and leave it that way and think that's going to work. It's an equal sign here. So you've got KEQ or KC or KSP or something along those lines. Make sure you incorporate that. So pretty simple, yes? Always do the easiest ones on here when you can. Just keep in mind that solids and pure liquids are never incorporated inside there. All right, the last one, number 3, I want to point out to you because, again, they wrote this as if it's an organic, we're in an organic chemistry class, which, again, I hate that. So here's the acid, and notice that the H they're taking off is this last one. Do you see that? Normally, this is acetic acid. We would write this HC2H3O2, right? And we would take the first H off, and we'd have the acetate ion. Yeah? That is the exact same thing. Exact same thing. This is just written in the format that you would use if you were dealing with it as an organic acid, which it is an organic acid, but typically this is how we see it. We're not in organic chemistry. So this is how you're going to see it here. But you need to recognize that CH3COOH, COOH, that's vinegar, acetic acid. Yeah? Yeah. CH3COOH. So this one they like to use a lot. So when we do this, it's still the same thing, products over reactants. Everything is aqueous. It's an aqueous solution, so everything's going to be incorporated in there. No, because this is not a solid.
Oh, okay.
Yeah. Ka, yeah. Yeah, they could use this and deal with this as KEQ, and they could just talk about, in general, they could talk about the concentrations here, but because it has this, that's what makes it an acid, and they could also talk about Ka, and talk about if we know this concentration, we could figure out what the pH of it is then. And again, since we had the whole COVID thing last year, I don't know how much you guys remember about calculating pH and POH and things like that. So again, just write the equilibrium expression. That's all they're asking you to do. Okay, flip the page. And on the next one, we have this equation, the nitrogen monoxide and chlorine gas combined to form, I think it's nitrogen hypochlorite, OCO. Yep. It was studied at 25 degrees Celsius. The pressures at equilibrium were found to be as listed. Calculate the value of Kp for this reaction. So, what's your equilibrium expression? Okay, so we have Kp, because they're asking specifically about pressures, right? Write the equilibrium expression. Do not put numbers in it. Write it as is with the formulas. Obviously, you're going to put some numbers as the exponents, but write it with the formulas of the substances. So Kp is equal to products over reactants. I'm not going to write a rice table because they've just point blank given us the concentration, so there's no need for a rice table. We have the equation, we put the numbers in the equation, we're done with that. If they're asking us for concentrations, that's when we need a rice table. So I have NOCl products over reactants. Oh, sorry, this is pressure, isn't it? And NO, and I put those backwards. I usually try to keep them like in the order they're written, but I just wrote those backwards, so don't worry. Just pay attention, you're putting the right numbers in the right spots.
Are they supposed to be brackets or
Parentheses, because it's pressure. Again, they're not going to count off if you put brackets. I mean, in standard format, we usually do it as concentration, but we can kind of, yeah, I don't think they're going to count off for that at all. So we've got 1.2 atmospheres, and it's squared. And notice I'm not putting in the units of measurement because K doesn't have any units of measurement. So I'm not going to waste my time doing that. I have the NO is 5 times 10 to the negative 2, and that's squared. And I have 3, I love this, 3 times 10 to the negative 1. Why would they waste time doing that for the chlorine? Pop that into your calculator. Is K large or small? Very large. So is it going to pretty much to completion? Yeah, products are heavily favored, it's going to completion. When K is over 1, it means that the products are favored. Okay, so if you look at number 7, that's where you have to convert KP to KC, and you are not required to do that anymore. They specifically took it out of the AP. I mean, they made even a comment about, hey, you're not going to have to convert from KP to KC and back and forth. So I'm going to cross off number 7 here. And then look at number 8. Number 8 is when they're talking about Q. I want to compare something here. At number 6 here, it says the pressures at equilibrium are this. They point blank gave us everything at equilibrium. If we compare that to number 8, first of all, they're saying we're going to use the reaction quotient, that's Q. For the synthesis of ammonia at 500 degrees Celsius, the equilibrium constant is this. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. They didn't tell us these numbers that were at equilibrium, right? They point blank said it's going to have to shift to get to equilibrium. So what we have to do is we have to find what we call Q, which basically is when it's not in equilibrium, what's the constant there? And then we take this Q and compare it to K. They've given us K here. They gave it to us right here. They gave us K here, and we're going to compare our number to that when we get it. So, first thing we need to do is they're going to call it the reaction quotient or the mass action. Is that what we called it earlier in the notes? The law of mass action? Was that it? Yeah, so they're going to call it something like that. Basically, when you see that they give you numbers and they're not in equilibrium, we're finding Q here. So when we have Q, write Q's equilibrium expression. Basically, it's the same basic thing that we're doing here. So we've got our balanced equation here, where it's for the ammonia one. So the synthesis of ammonia, so it's still the same equation that we used earlier. So we had H2 plus N2 right here. N2 plus 3H2 produces 2NH3. So we have N2 plus H2 produces NH3. If we balance that equation, sorry if I can balance that, 2, right? There's your balanced equation. It's just the production of ammonia. So here are the numbers they gave us. And we know it's going in this direction because it says for the synthesis of ammonia, right? So our equilibrium expression, or our Q expression, we would have NH3. And we're dealing with concentrations, right? Yep. And it's squared. And then we have N2 and H2 to the what? Okay. Now they're going to give us, they've given us the numbers, so plug your numbers in.
So is this like overall what like the equilibrium unit will be, or is this just the basics?
This is the basics. In most cases, you're going to have to do a rice table.
So like will we be doing more of the complex stuff?
Yeah,
after
so,
today,
yes, yes. So what you're doing here is you're getting the basic premise of just using the equation. What they'll probably do is they'll say, okay, instead of just giving you these numbers here, you're going to have to find those numbers. So they like to do it that way. They like to give you the K and have you find the concentrations. So we're kind of building up to that. Are you going to miss again?
No.
Okay.
I was just wondering.
Yeah, here's not so bad, right?
Yeah, because I was thinking,
Yeah.
I was like, this unit's pretty easy.
Yeah, here's not so bad. It's the rice tables that tend to throw people off. I personally, once you get the hang of the rice tables, I think they're okay, especially if you just remember that little trick where I said if it's less than times 10 to the negative 3, you can kind of get rid of some of the x's. Yeah. Okay, so the next one into is 1 times 10 to the negative 5. And H2 is 2 times 10 to the negative 3 cubed. Okay. You guys pop it into your calculator. So I squared my top one and then I just took that and answer divided by. And if you use your parentheses carefully, then you can just plug it in all in your calculator at one time. So just pay attention to how you're using parentheses. If that doesn't make sense to you, take a minute and write crap down. And then that way you can go ahead and plug it in your calculator here. But I got 1.25 times 10 to the... I got 7. Okay, this is Q. This is not equilibrium. This is Q. Okay, so I'm going to make my line here, right? Here is 1, right? And if I look right here, 6 times 10 to the negative 2, so it's 0.006. So when I look at this, here, where's K? To the left, so K is over here. Zeros, we don't care where 0 is. So K is over here, right? There's where equilibrium is. That's what the constant. This is not concentrations or anything. This is just K. K is over here. Where is Q? Way over here is where Q is, right? Notice this. Predict the direction in which the system will shift to reach equilibrium. Which way is it going to shift? It's going to shift to the left. That means it's going to shift to the reactants, right? That's what they're asking you about. So it's going to left shift to more reactants. That's what they're asking you for here. So you calculate Q the exact same way that you do K, and then you compare it. They've given us K. So when we look at this number line that I have here, it's all about K. Here's where K is. We just calculated a Q that was way the heck over here. Which way will it have to shift to get back to equilibrium? Yeah? That's what they're talking about here. Try letter B. Same basic premise, only they're giving you different amounts of stuff. They're saying, hey, here's the amount of stuff we have. Which way is it going to shift to get to equilibrium? So when they give you numbers that are not equilibrium numbers, and they're not initial concentrations, are they? If we have initial concentrations, usually something's going to be 0. And they're going to point blank say, hey, these are initial concentrations. They're not giving us that. They're saying, hey, we've got this much stuff in there.
It's going to be the same basic equation.
Mm-hmm. Yep. Yeah. Same basic equation, just different numbers. A lot of times, even if they don't point blank ask you to find Q, find it, because sometimes that's what they give a point for. So don't skip over that and say, oh yeah, I can just look at that and say, oh well, it's going to shift left or it's going to shift right or what have you. What'd you guys get?
0.06 million.
Yeah, so 0.06. Wait, now let's look at this a second. 0.06. There is no unit of measurement. Yeah? There's no unit of measurement. So let's compare this to K.
Wait, so there's no unit of measurement?
There is no unit of measurement. Okay, did you pop this in? Yeah, you might have hit. What'd you get?
0.02.
Okay, I think you hit a wrong digit. Yeah, you just hit a wrong digit. So look at this. Isn't 6.02 times 10 to the negative 2, isn't that 0.06?
Yeah.
So tell me about these two. Compare these.
Oh, they're the same.
So this reaction is what? This is at equilibrium.
Wait, so there's no like right side and left side?
No, there's not, because it's the same as K. If Q is the same as K, it means it's already at equilibrium. So see what they've got going on here? They're wanting you to compare, hey, this set of numbers, compare this, find what we've got, and then compare it to K and show that comparison. If it's the same number, there is no shifting. It's already at equilibrium. Yeah? Okay, I have several people that keep saying things about, well, no, it's 6 times 10 to the negative 2. Well, no, it's 0.06. They're the same number. It doesn't matter which way you put it. They're the exact same. Okay, do letter C. Did you square it? Did you put 3.54 times 10 to the negative 1? I just moved a digit over. 0.354, because it's the same thing. Is the same as 3.54 times 10 to the negative 1. And that's cubed?
Oh, it's cube?
Yes. Is that what it was?
Yeah, I squared it. Yeah, I got 0.06.
Okay, again, on letter C, same formula, same thing set up. Now we're going to find Q again.
Wait, what is it? I just pressed it. Never mind.
Okay, what'd you come up with?
1/500 or 2 × 10⁻³
Why would you say 1 over 500? We don't leave crap in fractions. We're not math class. Come on.
Yeah, Jerry did.
So you have 0.002, yes?
Yes.
All right. Which way is it going to have to shift to get to equilibrium?
Right.
It's going to have to shift. So if we have our K is 0.06 and we have this number is 0.002, it's going to have to shift right to get to equilibrium. So more what? Don't be afraid to, here's your equation, here's your calculation. Don't be afraid to put words with that. Questions? Okay, flip to the next slide, next page. Okay, so the reaction has been carefully studied at 350 degrees Celsius and Kc is 0.079. Which direction will the reaction proceed to establish equilibrium under each of the following conditions? Okay, so all of these are again that law of mass action. Okay, so if they say, and again, the whole reason I put that in there is because they popped that up on the test once. So they're asking for Q. It's the law of mass action. We don't know what these sections are, so what we're going to do is we're going to look at that and determine, is it going to shift right or left? So let's look at this. We have K is 0.079, right? Well, look at this. I have a 0 and a 0. So if I look at my reaction, this I start off with 0.1 molar, but these two are going to be zeros. What's the only way it can shift? It can only shift to the right to make more products, right? That's the only thing that can happen. We don't even have to do the calculations because what happens when you put zeros in there? Yeah. So it has to shift right. Now, in this case, we could say, and they might even ask you, is Q going to be greater than or less than K? Q has to be less than K. So here's K. Let's say here's 1, just because I felt the need to put it on there. K is here. Yes? That means the only way in order for it to shift right, Q has to be way down here, right? Q has to be less than that. So Q is less than K, and it's going to shift to the right. The only reason I'm putting it to you in these words is because they might ask it in that manner. Is Q less than or greater than K? Well, just look at that. If it has to shift right, then Q has to be on the far side of the number line of K. So Q has to be smaller than K. Q is less than K? Yes? Okay. Here, the next one, look at this one. We have, here's our reaction. We have 0, we have 0.1 molar, and we have 0.1 molar. What's the only thing that can happen? Yeah, look at this. If we have 0 of this, absolutely none, the only way it can shift is to the left. Correct? And it's going to do something because equilibrium is saying, hey, you're going to have some of everything, right? So when you have something where it's saying you've got 0 of that, well, it's got to shift in that direction. Maybe just a tiny, tiny little bit, but it's going to shift so that you have some of everything in here. So in this case, we have to have that shift to the left. In this case, what can happen here is here's 1, here's our K. If it's going to shift to the left in this particular setup, if we were to calculate this, would Q be greater than or less than K? It would be just a little bit greater than, right? Q's got to be over here if we have to shift left there. So Q, it may be a lot greater, it may be a little greater, but it's going to have to be a little bit greater than that if it's going to shift. So if we calculated Q here, then we would have something going on like that, although we'd have a problem with that, right? Those zeros screw everything up. Okay, look at letter C. Can we eyeball it and tell whether we're going to shift left or right? Can you? No, nothing's 0 at all. So this is a true equation where we have to solve for Q. It's not at equilibrium. They told us that up in the problem here. It's not at equilibrium. They're asking us which way is it going to shift to get to that. So solve for Q. And again, Q is the exact same equation as solving for K. So we have, write your equilibrium expression. First and foremost, always write your equilibrium expression. So products over reactants. Products over reactants. Products over reactants.
Oh, it's a decomposition.
Yeah. And notice they were snotty and used the little half number to balance it because they just want 1 molar of something. So plug your numbers in. So here, there's a point right here. I can guarantee you there's a point. They'll be on the test that you take over this. Writing the equilibrium expression is going to be one of your X's. There's a point right there. Writing the numbers in the equation may or may not. It just depends on what they want to give for you. Sometimes they have it in there showing the work, sometimes not. You can pretty much guarantee somewhere in that it's going to say, hey, they showed their work.
Do you have to put in all the zeros?
All the what?
All the zeros? Like, you just put 0.1.
I'm not putting in all the zeros. Just when you get your final answer, make sure you have the right number of sig figs. Okay, so immediately when I look at this, I'm thinking, oh, hey, I've got 0.1 and 0.1 on top and bottom. I'm going to cancel that out, right? So basically, you have 0.1 taking the square root of 0.1. What's the square root of 0.1? How many sig figs should I have on this? 3 sig figs on each one of these, right? So, which direction will the reaction proceed to establish equilibrium under each of the following conditions? So if it's 0.3, our equilibrium constant is 0.079. Which way will this shift? Left. Is Q greater than or less than K? Q is greater than K. That's why it had to shift to the left. Q was way over here. Is it still less than? Yeah, still less than 1, but Q is way over here. So it's greater than K. It has to shift to the left to get there. Yeah? Okay, do letter D. So did you get 0.079?
And it's all equal.
Okay, so Q equals K, no shift. Questions? Okay, number 10 is actually has nothing to do with equilibrium. It's just kind of a section in there that's talking. Let's kind of go back and review and kind of remind you. I'm going to skip that one if you want to go back on your own. It's just talking about delta H. I don't know. No, let's go ahead and do that. I'm thinking of the wrong one. This is one that's going on here. So let's go ahead and look at this. They're talking about delta H, but they're talking about increasing or decreasing the temperature. So in this particular reaction, delta H is negative 1036. Is the heat is it a reactant or a product? Okay, if it's negative delta H, it means it's exothermic, right? So I could actually incorporate the 1036 kilojoules on the product side, yes? Okay, given the reaction is equilibrium, predict the direction of the reaction will shift when it's disrupted by each of the following. So, if we increase H2O, if we increase the water, will anything happen? Look at the states of matter. It's a pure liquid. Is the pure liquid a part of the equilibrium expression? No. So that's where you need to be careful. And they'll do that. They'll throw those in there, and then they'll have to remind you, because we're thinking immediately like you did. I did the same thing Axel did. I looked at it and said, oh, it's a product that's going to shift to the left. But then you go back and look and say, oh, no, it's a pure liquid, so it's not in the equilibrium expression. Yeah? Nothing. Nothing changes, nothing happens. Yep. So what about if we increase the temperature? There you go. Think of the temperature, the heat, as a product, and if we add more heat, it's got to shift to the left. Yes? Okay, what about 3? Okay, so what's happening to the pressure? Is the pressure increasing or decreasing? So the pressure increases. Ignore this. Which side has more moles of gas? 5 moles, and over here we have 2 moles, right? So if we increase the pressure, we have to shift away. Yeah, we have to shift away from the greatest number of moles. We have to relieve that pressure. And the only way you do that is by producing less of a gas, less number of moles of gas. So in this case, if we shift to the right, we end up producing more water, yes? Less numbers of moles of gases, that means less pressure. Uh-huh.
So more.
We replace. Yeah. 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 So here on the 4th one, the amount of H2 is pay attention, because they're going to throw in a decreased in there, and automatically we think you put more. Increase. Just, I don't know why, but we tend to lean to that. So pay attention, this is decreased. So if we take some of this out, isn't it going to shift that way to replace the hole? To fill in the hole that we just left? Yeah. So we have a left shift. Okay. Go take a break.